Alright everybody, we're on chapter 9.1, which is graphing rational expressions. First thing I want to do is I want to start off with the most basic rational expression graph, and it looks like this. It's y equals 1 over x. I want to talk about this function for a little bit, and I want to establish a couple things. First thing we want to look at is the domain. The domain of this, now remember, domain is defined as all the values that x can or can't equal, depending on which one's easier for us to write. And so when we deal with fractions, we're trying to avoid any type of value that would turn the bottom into 0, right? Because we can't divide by 0 in math. It just causes a lot of problems. It's undefined by math standards. So when we say the domain here, we're going to look for all values that x cannot equal 0. Because in this particular case, all of the values are okay, but if I put a 0 in here, I'm going to end up with an undefined answer. So we want to make sure that we establish our domain. But let's see what happens here, because this is actually a very interesting graph. If I let x be very close to 0, right? We just can't get there, but we can get really, really close. We can get as close as we want to 0. So what I'm going to do is I'm going to choose a couple of values that allow x to be very, very close to 0, and we're going to see what happens to our values here. So if I let x equal things that are really, really close to 0, let's say something like 0.1. If I let x equal 0.1, well, what I have here is 1 divided by 0.1. Okay? And 1 divided by 0.1, let's call this x, let's call this y. Well, 1 divided by 0.1, that's 10. What if I let x be 0.01? Well, that's even smaller than 0.1. That's 1 over 0.01. That's 100. And I think you guys are going to see what's going on here. If I put another 0 in there, I get 1 over 0.001. That's 1,000. The funny thing is that the smaller I get here, the larger I seem to get on my y values. So what we can say is that as x gets smaller, y, what we say, increases without bound. Y increases without bound. Okay? But let's see what happens if I end up letting x get really close to 0 from the negative side, right? Because these are all positive numbers. Let me go and change to red to catch up. If I say let x equal negative 0.1, then I have my function 1 over negative 0.1. Well, that's going to be negative 10, right? And this is y. If I say negative 0.01, well, we don't have to do any more math for that. That's negative 100. And then in this example here, negative 0.001, that's negative 1,000. So as these numbers get increasingly smaller, closer to 0 on the negative side, right, closer to 0, these get, and I'll just call them negative larger. All right, and I know that's kind of a contradiction, but we'll just look at it as negative big numbers, right? So as x approaches 0 from the negative side, so as x approaches 0 from the negative, y, we say, decreases without bound. So what does that look like on a graph? What does that look like on a graph? I'll give you guys a chance to copy that down for a little bit. Go ahead and hit the pause button if you have to. I'm going to do the same. Okay, so we're back, and actually I want to go ahead and rephrase something here. We said as x gets smaller. I want you guys to be a little more specific and say as x approaches 0 from the positive, as x approaches 0 from the negative, y will increase without bound, y will decrease without bound. So don't use smaller or bigger. We say as x approaches 0. So what does that do? That creates this, what we call a horizontal asymptote. Okay, a horizontal asymptote. And if you can think about an asymptote kind of like a force field, All right, there's a point at which it'll never equal 0, but it'll get really, really close. So as we approached 0 from the positive side, the x's started getting really, really big, right? As we got closer and closer to 0, the y started getting really, really big. Well, as we approached 0 from the negative side, they started getting really, really, really small. They were getting very, very small, astronomically small, right? Negative 1,000, negative 1,000,000, negative 5 billion, blah, 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 closer to negative infinity, right? Okay, so let's see what happens when we let x get really, really large. If I allow x to become a very, very large positive number, now bear in mind, remember, our function is y equals 1 over x. So if I allow x to be 10, well, y is going to be 1 over 10. If I let x be 1,000, I have 1 over 1,000. If I let x be 50,000, then I get 1 over 50,000. My numbers seem to be getting smaller as x gets larger. So they will get smaller and smaller and smaller if I allow x to be, say, 1 with a bunch of zeros behind it. It's going to be 1 over 1 with a bunch of zeros behind it. So what we say is that this function, as x increases, y gets closer to 0. Now, just because it gets really, really close to 0, remember, it's always going to be 1 over, say, some very large number. It's going to get very close to 0, but it's never going to get there. All right, it's never going to get there. And so what that creates is that creates this sensation called the horizontal asymptote. All right, it creates a horizontal asymptote because we're creating this zone around 0 that the function will never get to, but it'll get really, really close. Similar to the vertical asymptote, how it gets really, really, really close to 0, but it can't ever get there. It's going to get really, really close to 0 on the x-axis, but it's never going to get there. And just like on the negative side, it's going to get really, really close to that horizontal asymptote, but it'll never touch the x-axis. All right, so that is the first graph that we're going to deal with. All right, we're going to do many, many more. Hang on. Okay, so now that we understand the basic dynamics of the rational function, we're going to do a bunch of examples of these rational functions. And with each rational function, I'm going to go ahead and identify several things. What you want to identify is you want to identify the vertical asymptote, which I'll abbreviate as VA, the horizontal asymptote, the y-intercept, and the x-intercept. All right? So the vertical asymptote here, it always has to do with the bottom. Vertical asymptotes always come from the bottom, issues with domain. Well, what value will allow the bottom to equal 0? Well, if I allow x to be negative 2, what that does is it turns the bottom into 0 and we can't go there. The horizontal asymptote will occur in the function's end behavior. So as x gets very, very large, as we saw a couple seconds ago, what's going to happen to this whole thing? Well, as x gets really, really large, 1 over a big number, well, that's going to approach 0, right? Because as x gets really, really big, 1 divided by a really, really big number is just going to keep getting smaller and smaller and smaller, and it's going to hit 0. So 0 is where my horizontal asymptote occurs. The x-intercept, I find the x-intercept by allowing x to equal 0. So 1 over 0 plus 2 is 1/2. So I'm going to say 0, 1/2. And my x-intercept is when y equals 0. So if I let y equal 0, 0 equals 1 over x plus 2, I can't solve that because 0 can't equal 1, so that's done. So there is no x-intercept on this one. Now, we learned a couple days ago about the sign chart. Now, the sign chart's really, really good in helping us figure out where functions are negative and where functions are positive. That sign chart's going to come back again today in conjunction with this table to help us graph. So, my critical numbers in a sign chart, right, are where the function becomes undefined or equals 0. There is no place where this function equals 0, but there is a place where it's undefined, and that is negative 2. So negative 2 becomes my critical number. I'm going to partition it down, and I'm going to put both of my functions in there, so 1 and then x plus 2, and I'm going to evaluate where it's negative or positive. If I choose a number beyond negative 2, well, this is the only thing that has the variable. 1 is positive no matter where I put it. Beyond negative 2, if I choose negative a billion, this is going to be negative. If I choose a number beyond 2, if I choose 0, 0 plus 2 is positive 2, or more importantly, it's positive. Well, a positive divided by a negative is negative, and a positive divided by a positive is a positive. So let's see how that impacts our graph. Okay, here's what you guys are going to do whenever you graph these things. I want you to draw in all of this information first from this little table right here of your vertical, horizontal asymptotes and all that good stuff. We know we have a vertical asymptote at negative 2, so go ahead and just draw your vertical asymptote. We have a horizontal asymptote at 0, we know that. Our y-intercept is 0, 1/2, so that's right there. Okay, before negative 2, which I'm going to go ahead and redraw as my green, before purple rather, before negative 2, which is right here, right? Before negative 2, this thing was negative, which means that it is below the x-axis. Below the x-axis looks like this, right? It's got to maintain below the x-axis. It can get really, really close to the horizontal asymptote, but it can't cross it. It can get really, really close to the vertical asymptote, but it can't cross it. Now, beyond this purple dot, which is my negative 2, the whole function was positive. So positive, and remember, it crosses at positive 1/2. That's where this red dot is. And so it approaches the vertical asymptote, never gets there, but gets really, really close, just like it approaches the horizontal asymptote and never gets there. Okay, but it gets really, really, really close. All right. Now, I know that this is a little bit confusing, but eventually it starts to get a lot easier. Let's do another example. Okay, so let's take a look at this example here. I've got y equals x plus 4 over x minus 1. Oh, hey, Devin, how's it going? Sorry, I've got a float builder in here. Hold on for a second. Sorry about that. That was Devin Rosario, my class president. Hold on for a second. Okay, so let's identify the same things. We got vertical asymptotes. We got horizontal asymptotes. We got a y-intercept. We got an x-intercept, maybe. Okay, so vertical asymptotes occur where the function is undefined. So it's undefined down at the bottom. If I set x equal to 1, I have a vertical asymptote because I have a 0 on bottom and you can't do that. Now the horizontal asymptote, this one's a little odd. If I rewrite this function down here, y equals x plus 4 over x minus 1, let's say if I plug in big number here, if I plug in the same big number here, what you guys have to realize is that the larger x gets, billion, trillion, 10 trillion, 100 trillion, all those big numbers, this 4 and this negative 1 become very, very inconsequential, don't they? I mean 100 trillion and 4 versus 100 trillion and negative 1, there's not much of a big discrepancy. So as these numbers, these x values get really, really large, these numbers here become very inconsequential. All right? And so what we really have here is one really big number and one really big number also. So the end behavior of this function approaches 1 divided by 1. In this case, the horizontal asymptote is going to occur at 1. All right? Hopefully that wasn't too confusing. The y-intercept occurs when x equals 0. So if I put in a 0 under x and a 0 under x here, I get 4 divided by negative 1. That's negative. Oops, sorry, not going to jump that far ahead. 0, negative 4. And my x-intercept is going to occur when I let y equals 0. So that's 0 equals x plus 4 over x minus 1. If I multiply by x minus 1, that's going to go away. Subtract 4 from both sides. X-intercept is going to be at negative 4, 0. Okay, like I said, eventually this is going to get a lot easier, but sometimes it just takes about 5 or 10,000 of them. That's what One of my martial arts teachers used to say, about 10,000 punches, you'll learn how to punch with your elbow. Okay, now that we have all this information here, let's pump this thing into the sign chart. The sign chart, remember, the critical numbers of this function are where the function is going to equal 0 or where the function is going to be undefined. It's going to be equal to 0 at -4, and it's going to be undefined at 1. So let's go ahead and partition this thing. Okay, let's put in both of our functions, x plus 4 and x minus 1. Okay, beyond -4 to the left, -1 billion. I'm going to get a negative number here and a negative number here. In between -4 and 1, I've got 0, so that's going to be a positive number and a negative number. Bigger than 1, I'm going to get 1 billion, so that's going to be positive, and that's going to be positive. So my final intervals are going to be positive, negative, positive. Now this helps me determine whether or not I'm above or below the x-axis. So let's graph this thing. Okay, let's draw in our asymptotes first. My vertical asymptote is at 1. My horizontal asymptote is at 1. Okay, so let me go ahead and draw in a point of my critical number. We did that in purple the last time. Okay, so at -4 is a critical number. So 1, 2, 3, 4. Okay, and that also happens to be my X intercept. My y-intercept is 0, -4. So let's go ahead and draw a point at 0, -4 in red. 0, -1, 2, 3, 4. Okay. The other critical number occurs at 1. Well, at 1, that's where my asymptote is. So that's my other purple dot. All right? So let's see what happens here. Before -4, I'm positive. So I'm above the x-axis, but just barely, right? Because I can't cross that asymptote right there. So I'm just barely positive. Nevertheless, I'm positive. After -4, I am negative, which means I am below the x-axis. And notice how it also crosses at -4, my y-intercept. And so it's going to cross there, and then it's going to do this thing. All right? It's going to get really, really close to that vertical asymptote, but it's just not going to get there. Beyond 1, this other purple dot, I'm just straight up positive. So we know the behavior of these rational functions, so here we go. It looks just like that. All right? Let's do another example. Okay, let's do another one. So we're going to go ahead and identify everything that we can about it, and hopefully you're getting the hang of it. But if you're not, it's not a big deal. It's we will do thousands and thousands of more of these. My vertical asymptote occurs where I'm undefined. So I'm undefined at 2. My horizontal asymptote, remember, that has to do with end behavior. So as x gets really, really large, what I have is -3 over a big thing, and that big thing just so happens to be getting squared. Well, when we square things, they get even bigger. So what that means is that this thing is going to approach 0. Now, my y-intercept occurs when my x equals 0. So that is, let's go and just figure this out. -3 over -2 squared, that is 0, 3 over 4, which is negative. My x-intercept isn't going to exist because if I set 0 equal to the equation, if I multiply everything by x minus 2 squared, I get 0 equals -3, so my x-intercept does not exist. Okay, so let's go ahead and graph this thing. Or rather, let's do the sign chart. Whoops. Okay, so let's go ahead and do the sign chart for this thing. Now, in the sign chart, my only critical number is going to be 2 because there is no place where this function equals 0 because I have a horizontal asymptote there, but it does very much become undefined when I send a positive 2 rather in there, not a -2. And let's go ahead and put in our functions, -3, and let's go ahead and put in x minus 2 squared. Okay, so all I need is a number that is beyond beyond positive 2. So let's put in 0. Well, any number within this function here, x minus 2 quantity squared, is going to be positive, right? If I put in negative a trillion, I'm going to get -1 trillion and 2, and if I square that, it's going to be positive no matter what. So any type of squared function is always going to jump out positive. Well, -3 is going to be negative no matter what. I can't plug anything into that. -3 is just going to be negative. So my two intervals are negative and negative. So what does that look like on a graph? Let's go ahead and find out. I have a vertical asymptote at 2, so let's go ahead and pump that in. I have a horizontal asymptote at 0. I have a y-intercept at negative 3/4. That's kind of like right here, 0, negative 3/4. And so if I'm negative below, that means that I'm below the x-axis, and I'm negative before 2. And remember, this 2 here is this purple dot. The purple dot is what my critical numbers are. So I am going to be below, and as I approach, I'm going to cross negative 3/4 because that's my y-intercept. And as I approach this dotted line, I'm going to get very, very, very close to 0, or very, very close to the asymptote. Beyond 2, I am still negative. And so your function looks like this. Okay. Let's do a couple more. Okay, let's take a look at this next example here. So as always, we're going to do the vertical asymptotes. Vertical asymptote is going to be at negative 1. Horizontal asymptote. Okay, let's take a look at the end behavior of this thing. So if I go y equals 5x over x plus 1. Remember, as these numbers get really, really big, that plus 1 really doesn't matter that much. So let's say x was a big number, and x right here is a really big number also. Well, this big number up top here is being multiplied 5 times faster than the number on bottom, which means that my coefficient on bottom, being 1, will have an asymptote at 5 over 1. Okay? And now my x-intercept is going to be wherever this thing equals 0, so it's going to be 0 over 0, so that is 0, 0. And my x-intercept is going to be 0, 0 also, because if I set this thing equal to 0, 5x over x plus 1, well, that's going to cancel. Divide by 5, that's going to cancel x equals 0. All right? So let's go ahead and put this thing in a sign chart real quick after I delete this thing. Okay, let's put this thing in a sign chart. So my critical numbers are where the function equals 0 or is undefined. Well, it's undefined at negative 1, and it equals 0 at 0. So partition it down. And let's go ahead and pump in both of our functions here, 5x and x plus 1. So what we've got is, when we put in a big negative number with 5x, we get a negative. We get a negative here. In between negative 1 and 0, let's say negative 1/2, I'm going to end up with a negative here and a positive here. Beyond that, it's going to be double positive. So my final intervals are positive, negative, positive. So what does that look like when it's translated onto a graph? So we draw our asymptotes first. Our asymptote is at negative 1, so a vertical asymptote here. My horizontal asymptote is at 5, so that's 1, 2, 3, 4, 5. That's there. So this is kind of a higher asymptote. My x and y intercepts are at 0, so that's all I really need. Okay, so let's take a look. Beyond negative 1. So negative 1 was my first critical number. So negative 1 is right here where this purple dot is. I'm all positive. All right, well, let's use some common sense here. The only way I can stay positive and stay within the asymptote and not cross down into this negative zone is if the function exists up here like this. Now, at 0, 0, I have a y-intercept and an x-intercept, and it starts off negative between negative 1 and 0, so this is my negative zone between negative 1 and 0. It's going to cross, and then it becomes positive again at this positive part, and then starts approaching the horizontal asymptote. And there you have it. Let's do another example. Okay, here we go. Vertical asymptotes. I hope by now we can understand that there's 1 and -5. Horizontal asymptotes, because these two are going to get really, really, really large, it's going to approach 0. Y-intercept, well, that's if I let both the x's equal 0, so that would be 3 over -1 times 5. So that is 0, comma, -3 over 5. And then my x-intercept does not exist. Look back to some other examples for as to why. Sorry, that's Mrs. Stone texting me. Hold on for a second. Okay, sorry about that. We are actually in the middle of float building right now for homecoming, so that's why I'm having to pause so much. Okay, so let's go ahead and draw this out on our sign chart here. So my critical numbers are going to be at -5 and 1, and I'm going to go ahead and partition this down. And then, remember, there's no place where this thing equals 0, so all my critical numbers are where this thing is undefined. So let's go ahead and put in our functions here, 3, x minus 1, and x plus 5. 3 is a piece of cake because it's going to be positive all the way across. Negative a billion is going to be negative, negative. Between -5 and 1 is 0. This is going to be negative, positive. And then positive a billion is going to give us positive, positive. So my final intervals here are positive, negative, positive. So let's see how that looks on a graph. So hopefully the speeding up isn't really affecting anything that much. Let's see. Let's go ahead and draw our asymptotes. Our asymptotes, we have two vertical asymptotes this time. So at -5, so -1, 2, 3, 4, 5. So at -5, I've got a vertical asymptote rather, and at 1, I've got a vertical asymptote again. I've got a horizontal asymptote at 0, so let's go ahead and draw that. Okay, this is kind of a funky graph here, but let's just follow the sign chart, and it will not lead us astray. My y-intercept is at 0, -3/5, so that's kind of like right here. Okay, here's why the sign chart is so powerful. Because beyond -5, again, my critical numbers, I always draw a dot with a purple. Beyond -5, which is right here, I'm positive. The only place I can stay positive is here. And that's going to be an arc drawn this way. Well, let's take care of the other extreme. Beyond 1, which is going to be this asymptote here, I'm also positive. Right? So that is going to be above the x-axis, and that's going to look kind of like this. It's almost a mirror image of what we just drew over here. Now, between -5 and 1, I'm negative. Right? And so what that creates is it creates this sensation of a graph that kind of does something like this. And the reason why it shoots down is because it's going to be straight up negative, and it also has to pass through this y-intercept and get really, really, really close to that vertical asymptote. And so your graph kind of looks like this, which is kind of neat. All right, one last example, and then we're done, I promise. The reason why this function is different than all of the others is because it's going to have what we call a removable discontinuity. Okay, and I'll show you why. Because if you notice, x squared minus 1 can be factored into x plus 1 and x minus 1, and that's all over x plus 1. Well, what you notice is that these two things go away, and I end up with y equals x minus 1. Well, this is just a line. Okay, so we can graph a line. That's a piece of cake. It's just a line that has a little bit of a catch. Well, remember, this function was undefined at x equals -1. All right, so let's keep that in mind as we graph this thing. We have a line here that has a y-intercept of -1, and it's going to shoot up this way because the slope is 1 over 1. Now, at x equals -1, I have what's called a removable discontinuity. All right, and so if I go down 1 to the left 1, there's going to be a hole there. And that's because this hole is created by this cancellation. Okay, and that's about the only example I'm going to do of that. The rest I'm going to do in class because I don't want to bore you to death. So we will see you in the next video, or we'll see you in class. See ya.